Heath-Jarrow-Morton framework model. So everything I'm going to say is in the context of this framework. So remind you, this is a framework of looking at the complete term structure of interest rates as one entity moving in space. So this is a yield curve which evolves and not just up and down, but it may rotate and behave like butterfly and all the possible movements of the interest rate. So the notion is conceptually mathematics of term structure of interest rates is difficult. And so we, of course, try to simplify that. So I will tell you about one more model, which is extremely important and interesting as well. And then in the second hour, we will start credit risk. Okay, so remind you that in the Heath-Jarrow-Morton approach, the bond prices which are building blocks for all the financial quantities we are going to price. So if you are able to construct a zero coupon bond price basing on our model parameters, we are happy. So that's okay. So bond prices are differentiable. F is logarithmic derivative of zero coupon bond prices called forward short rates or forward rates, and they follow Ito dynamics. So with drift term and diffusion term, and moreover, in order to keep the market arbitrage free, the drift term from this page here must be expressed in terms of the diffusion in such an integral form. Okay, so we've heard a lot about various short rate models, about BGM model, and I used to call it Libor market model, but these days Libor is a forbidden word. So that was probably reason for the success of the BGM model, that we were able to recapture the market practice of using Black 76 formula. And then I've told you something about pricing of swaptions. And then let us move to next very important model by some people called Cheyette, by some quasi-Gaussian.
So, sorry, there is a question in the chat.
Yes.
Do you want? Okay.
Yeah.
The question is: you were speaking about movements of the curve. How do you extend Greeks, delta, beta, etc., in these multidimensional BGM settings, and how to compute them?
So that's of course an issue. So Greeks are not in that terms just numbers, but families of numbers. Yes, so volatility consists of several parameters, and the derivative Okay, theta, so derivative with respect to time is a number. Yes, so there is no problem. We calculate theta exactly the same way as in the FX equity market. But it was here. Yeah. Vega, so derivative with respect to volatility is a matrix, because volatility itself is a matrix. Sigma is composed of many parameters. And we call it normally bucket Greeks. So they are not numbers, but vectors or matrices. So to control all that's a problem, and practically they are collapsed some way to numbers, but you know, you may hide a lot of risk in that terms. So that just depends on the company, how are your regulatory Greek parameters. So that's not a science, this is practice. Okay, so maybe we'll continue with the Greeks later. But there is no standard. So there is something, an organization, a page called Totem, TOTEM, where the community tries to collect all the standards. Standardized methods of pricing, of calculating sensitivities and so on. And I don't advise anybody to be a slave of Totem, but it should be taken into consideration. So I think that's a good practice to know what a standard is and take it into consideration. Okay, so let's move to the last model, which is called Cheyette or quasi-Gaussian. I don't know why quasi-Gaussian. It's nothing Gaussian there. And which is an attempt of collapsing the large, maybe infinite even, dimension of the yield curve to a low number of parameters. So maybe even not low, but controlled. So to make a to have a 1, 2, 3, or 4-dimensional Markov processes, which, as I told you, make life possible. So computer calculation is always in low number of dimensions. So you may say, you've got short rate models in dimension 1. Okay, they are, so they follow one condition. It is in a very low dimension, dimension 1, but there is one but, they are not flexible. So Vasicek, Hull and White models looks like that and not differently. So it gives us a given shape of volatility. So when it coincides with the market, it's good. When it doesn't, it's bad. But we cannot do anything. We've got no flexibility. The same with Coxinger, Soros, and Black Karashinsky. The Cheyette model is flexible. So we may reproduce practically any shape of smile from the market. So it's a massive upside of the model. Okay, where is the assumption? The assumption here in the Cheyette model is separated volatility. So volatility of the Heath-Jarrow-Morton model, as I told you, is the parameter which determines the model, is of that term. And we assume it is just a multiplication of two functions, a function of little t and function of capital T. I presented it in that form, but knowing basic algebra, you won't have any problems. That's just notation. And this is equivalent to such representation. Then let me try to do on the slides to do something what may be relatively clearly done on the blackboard. And here, okay, probably you have to believe me, but if I convince you a bit, that will be a success. So then we integrate. We put an integral here from t to capital T. So we get the capital sigma, which is integral of, we integrate with respect to capital T. So V of t remains unchanged, and t is replaced, ht is replaced by its integral. I didn't, probably I didn't mention that V of t may be a stochastic process. It doesn't have to be a deterministic function, but h, of course, is a deterministic function because this is not, doesn't evolve with time. So that must be a function. Okay, and then taking again this integral here, this stochastic differential, we represent that in the integral term, and just integrate with respect to little t once more. Getting that term where h is so defined and y is so defined. So that's probably, when you know a bit 19th century mathematics, people could guess some representations of functions, special functions by other functions. So that's very laborious mathematics. Now we are educated in functional analysis and say more philosophical, logical approach to mathematics and not writing down symbols on a piece of paper. But okay, Orange Cheyette did it and did it very quickly because the paper was published the same year the paper of Heath-Jarrow-Morton. But probably, okay, many people had it as preprint before because the research of Heath-Jarrow-Morton was done, say, at least 3 years before publication of the paper, as in the case of Black and Scholes. So revolutionary papers are not published quickly. All right, so check it out or believe me. And then we integrate once more with respect to capital T and get the formula for zero coupon bonds, which is again the function of these two parameters, x and y. And it looks relatively pretty. It's not that ugly. Okay. And reminding that k of t is logarithmic derivative of h, we've got such a two-dimensional Ito equation for x and y. So people say this dimension is not 2 but 1.5 because only x is a full Ito process. Y is just doesn't have the diffusion term, only drift term. So why, when you, okay, you should work a bit with Cheyette model to understand what I will say just now, that Y is called convexity adjustment. So this is the less important part, but and sometimes omitted or replaced by a very rough approximation. Okay. Irrelevant. So when we've got here such an equation, such an Ito equation with the diffusion term V. And as V, we may set everything. So another stochastic process. In that case, we have stochastic volatility. V may be a function of x and y. Then we get a local volatility. So if we make such a choice with V, we've got two-dimensional dynamics of the yield curve. So I call it, don't know, skeleton driving factor of the whole yield curve. So this is a very similar situation as in the short rate models, when one parameter drives the whole yield curves. Here, there are two parameters, or 1.5. So, and we've got this crucial closed form formula for zero coupon bond prices. What's essential in pricing? So you may ask, what's better, what's different from short rate models? So you may show me this model is worse because the dimension is 2 and not 1. Yes, in that terms it is worse, but in another one it is better because the function v may be practically any. So we are very close to the pure local volatility when we have got one-to-one representation between option prices and volatility function. Yes, so, and this is the task of that model. So this is the reason why that model was developed, although Cheyette didn't know it because the model was created some 30 years back, and the pure formula for interest rates is relatively new. Okay, so one more important class of time structure models, and it's time to ask the first question to the audience. We are in the field of stochastic modeling of random functions. When somebody says important class of models, what's the answer? Consisting of one word. Try. Gabriel Garcia, for instance. Alessandro Ponti. Nobody?
Nobody.
Nobody takes a chance. So the answer is Gaussian. So when someone says about models of random phenomena, so the first answer is Gaussian. There's, I think, no field of probability here or applied probability where Gaussian models are not applied. They are very convenient and quite reasonable. So what does it mean, Gaussian models? This is, of course, the model where forward rates are, distribution of forward rates is Gaussian. What does it mean? And of course, if forward rates, distribution of forward rates is Gaussian, then distribution of zero coupon bonds is what distribution? Log normal. Yeah, because exponents of a Gaussian variable is log normal. And what does it mean in the modeling term? That volatility here is deterministic, and drift here, which is determined by the volatility, but okay, is deterministic as well. This is average here of the random variable, and this is standard deviation. Perfect. And of course, Gaussian models in the world of interest rates are important, popular, well developed. So you should learn that. And what is one more upside of Gaussian model, you can have it in various tastes. So one way, so Gaussian model is Gaussian model, so they all coincide in some sense, because if the distribution of forward rate is Gaussian, so and all the models are within the Heath-Jarrow-Morton framework, so it must be like that. It must be a drift which is deterministic and volatility with deterministic diffusion term. But we may use various approaches developed during this lecture. It was rather complete, so I didn't omit too many important things. Okay, so first approach is just take Heath-Jarrow-Morton. Put some deterministic function, sigma is volatility. So capital sigma is the integral of sigma times sigma, so it's easy to calculate. And we get a formula for forward rates, zero coupon bonds, and you are able to derive all the option price. Easy. And next, but we may make a step further and I'm reminding you that forward LIBOR is so related with the forward zero coupon bond prices. So this is definition for the model. So I've told you before about displaced forward LIBOR model, which may better capture the skew than the original one. Yes, it was yesterday. So that may be a surprise for somebody that Gaussian Heath-Jarrow-Morton model is a special case of displaced LIBOR market model. So first we came from Heath-Jarrow-Morton to LIBOR market model, sorry, not LIBOR market model, where LIBOR is forbidden, BGM model, and then we go from BGM to Heath-Jarrow-Morton. So here, of course, the sigma is a deterministic function. And, but we've got dynamics for forward LIBORs, not for and we may use all the forward measure machinery to get option price. But that's not all.
There is a question in the chat. Yes, I read. Displaced BGM, could you explain how the smile moves in the direction of underlying?
Displaced Libor market model was somewhere here. Blah, 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 blah. Yes, it was here. So, as you remember, my talk about FX and equity options. Yes, and what was the problem, which is as well in the interest rate world, that option prices don't want to follow a very clever model which was rewarded by Nobel Prize. But still the prices don't respect that fact. And when we take implied volatilities from the market, they are not flat, but they form a shape called the smile skew of the market. So the distribution of underlyings is not log normal. And I proposed one of best methods of modeling the skew was displacement. So is to shift a bit the underlying, that we don't model the stock price, but stock price plus a deterministic number. So in this case, we don't model forward Libors, but forward Libors plus a small number or a big number. And it is a surprise that Gaussian Heath-Jarrow-Morton model falls into this framework. So this is like BGM model displaced by rather a big factor, not a small one, but a big. So that just simplifies algebra and calculations. And of course, give us some way to think about modeling. Okay, so, but that's not all. We've got Hull-White Vasicek model, which is, for my knowledge, still used by several houses in that form, but you see the downside of the model, which is this fitting initial yield curve term. So that makes calibration of the model more difficult. So of course, it was first done by Hull-White some 30 years back. So then it was a real achievement, but now we know much more. But several houses still do it. I don't know. And one more final step. We've got here a Cheyette model, which was practically, I've done several calculations, and if in the case of Cheyette, here we assume that the volatility V is deterministic as well.
There is another question related, well, that from the same student. Just a moment. What about AT? It is calibrated as well.
What is
A of t? The coefficient A of t.
Where is A? Which A? Because no.
Yeah, I suppose it's this one.
Yes, mean reversion parameter in Hull-White.
Yes.
Yes, it is calibrated. It is calibrated because with A, we slightly move the Gaussian process. So, of course, A is not, as far as I know, in practice, is never time dependent. So in theory, it might be time dependent, but in practice, it's never time dependent, but it is calibrated, yes. So A in the Hull-White model represents for, of course, it's Gaussian, but there is some freedom to fit option prices away from the money. And with A, we manipulate to fit the smile a bit better. Of course, we don't have much freedom, but there is still some. So A is calibrated, yes. Positive answer. And then final step. So with the Cheyette model, when we assume that the V volatility was deterministic, then of course, K's got a closed solution. Yes. K, okay. In practice, in theory, it may be time dependent. In practice, it is not, it is a number. So look, these two models are very similar, but of course we don't model exactly the same notion. Here we've got the short rate, which follows the such dynamics. Here, this is a centered short rate. So short rate minus initial condition to start from the zero. So it's practically the same model, but with slight difference. But that difference is that for the Hull-White model, we've got complex formulae for zero coupon bond prices. And for Cheyette, we've got this formula, which is much easier. And I've noticed a trend that more and more houses replace the Hull-White model by Cheyette, and it is called normally linear Gaussian. And we don't have to fit the initial yield curve because it's incorporated already in the model. So that's much easier to handle. Pat Hagen promotes the linear Gaussian model. He's right. You may ask me, why I know so much about standards. Okay, they're probably not current, but some years back. I used to audit models in banks at some stage of my professional career. So probably I'm not authorized to say which bank uses what model, but say some statistics saying that that's typical, not typical, most houses, some houses. I think I don't break any rules. Okay, the last part of the of my interest rate talk is about local volatility for interest rates, which was justification for the Cheyette model. With freedom with the local volatility, we could replace the Cheyette trick, that linking market observables here with model parameter by a closed formula. It's not that easy, but okay, let's try to do again. That for, I've got still some time, for the interest rates, but with slight changing of the notation. So to, computers think in discrete time. For computers, everything is discrete. But humans prefer to have differential equations rather than difference equations, continuous times. This is, I don't know, a property of our mind. So to derive some equations, I will change a bit compounding from discrete, which was discrete compounding for the, somewhere here. No, that was swaptions. Yeah, here we had discrete compounding, so sums of zero coupon bonds. Yes, and now we are moving to continuous compounding. In practice, it's doesn't change a lot. And when we make numerics, when we calculate everything, and we have to discretize, so we are back at the starting point. So that's only to have differential equations. And so this is the annuity and swap rate in that form. Swap rate from little t to capital T plus little t. So the swap tenor is equal capital T. This is this equation. And the swaption price is as it was defined before. So discounting, annuity, and intrinsic value of the swaptions. And then again, let us define by D. This is discounting riskless asset. This is discounting risky asset. We've got formula here. And again, let us use the eta formula, which during this lecture was used probably 100 times. So for D, This formula, trust me, it was calculated and published and reviewed, so that that term should be true. And that this is the Ito differential for the risky asset. And now, let us, as in the case of the Dupuy formula for equities, let us calculate discounted intrinsic value of the option. So, first term is the Dirac delta times what's inside here, plus that term, that Heaviside function of indicator that S of t greater than t times differential. So exactly the same procedure as for equity DPR. Then we take expected value and get the following formula.
Sorry, there is a question in the chat.
Yes.
It says, in another class, we were told about counterparty credit risk. Which of those models are efficient to compute exposures?
All of them. All of them, but there is, I will talk about it later. Later, I think tomorrow, because today I would like to tell something different. There are some practical problems related to credit risk. Why some models are used and some models are used and should not be used. That should not be used from theoretical point of view and are used in practice. So later, be patient, tomorrow. Okay, so we've got formulae for the expected stochastic volatility. And finally, we may link this Dupuy calculation to any of our models. So the best suited is Cheyette model, because we've got in the Cheyette model, we've got the V, which is a function of X and Y. And we've got here the Dupuy formula, which links various volatilities. So I think, ladies and gentlemen, that is. So I swear, I may be wrong, but I've told you the most important practical, but with theoretical flavor, things about interest rate modeling. With the equities, that was, say, 50% of important things. But for interest rates, it was 90%. So now we've got some minutes for questions. The lecture will be devoted to credit risk. So there were several questions from the audience about credit risk, so I should consider that topic seriously. Okay, so I will speak about single name credit risk, multi-name credit risk, and the last probably, I don't know, half an hour of the lecture will be general and loose thoughts of a mathematician in a bank. It is worth doing, not worth doing, so what you will get, what you will pay for. So it's called sharing an experience. Okay, so what is, from mathematical point of view, credit risk? So credit risk is a theory of a stopping time. So of positive random variables. Yes, so something exists and then stops to exist, or still exists, but something is changed. Theory of credit risk is theory of random events. So in the first, the most naive setting, default time is just a positive random variable. Yes, so what a simple, naive 19th century mathematician do it. So we may calculate probability of that. Yes, we make take logarithm of that probability. We may differentiate it. And what we get, this will be the hazard rate. So the instantaneous probability that the entity defaults at time t, provided it didn't default up to now. And if you want to be a bit more mathematical, we may say that this term, so the indicator function that we didn't default yet, plus integral of the hazard rate, is a martingale. And in such a simple word, we may say quite a lot. So there is a field of mathematics engineering called reliability theory, which is theory of credit risk, but for physical engines. So not company defaults, but something breaks down. And it was developed in the 19th century, first half of the 20th century, with mostly by engineers and not mathematicians. So that was very simple, and there are quite tight books about such mathematics. So that's not trivial. And what are products exposed to credit risk? So stocks and shares are not. Stocks don't default. When a company goes bankrupt, the price of stocks goes down, but we cannot call it default. So it's got some value, and it may change. The company may be restructured. So we are not saying that stocks default, but bonds, of course, may default. So the situation, non-defaulted bond pays its nominal at the end, so it's an obligation. When a company says we are not able, we will pay you something, but we're not able to pay the full nominal, not speaking about the interest, it is called default. And the simplest but most popular credit risk instrument is called credit default swaps. So this is a product where one party, say, let's call it insurance, one party pays some coupon on the yearly, semi-annually, or monthly basis. And in exchange, this party gets from the second party a part of the nominal, so full nominal or nominal times loss given default from the second party. So an insurance contract for your car looks identical. So, of course, credit default swaps may be traded. There is a market. They are much less liquid than interest rate swaps. Any idea from the audience why? Anyone knows? I know, of course, because number of governments is much smaller than the number of companies. So a government issuing a bond, so the potential, even if we say that number of potential biases is more or less equal, so that amount of money is distributed among smaller number of entities. So what's the consequence of credit default swaps? That credit default swaps are less liquid. So in consequence, there is nothing like swap stripping for interest rate swaps. So we try to put constant spread for all maturities for the credit default swaps, or create an interpolation. There is much more guessing, so the market gives us much less information about the product. Okay, so after that elementary mathematics, say analysis 1 or secondary school, let's jump to second half of 20th century and use the modern theory of stopping times. So stopping time is a positive random variable with some relation to the increasing family of sigma fields called filtration. So roughly speaking, not mathematical words, that means that stopping times are measurable with respect to to the filtration, so that don't predict the future. And there is, I think, this is Professor Dolan's dad, who maybe Paul-André Meyer, who did this classification that stopping time is predictable if there is a sequence of stopping times such that they tend to this stopping time, and is totally inaccessible if there are no such stopping times that may approach the stopping time tau. And the theorem is that a stopping time is either okay on some parts of the probability space, either predictable or totally inaccessible. So what is the practical consequence for the market practice of such a setting? Because this is mathematics safe from Strasbourg, Paris, but we are speaking about practical things. So in practical terms, that gives us two ways of modeling of default times. So one is structural models, where we get a stochastic process describing, I don't know, company assets or its state one or another way. And the company defaults when the assets fall above the level of debt, for instance, or some other criteria. Yes, and such stopping times are, of course, predictable because we may predict the moment of default. So, our assets are just above the level of debt. Now it's worse. We've got only $10,000 above the level of debt. Then, bam, our assets are less than the debt. We must declare insolvency. So this, I would say, these are a kind of internal default types. So those which may be maybe not exactly predicted, but the process of deteriorations may be observed. And the second, where we have totally inaccessible stopping times, are reduced form models. So an example is jump of Poisson process. Yes, because we are in perfect mode, everything is good, the company is highly profitable, and then bam, that pandemic appears. Our planes don't fly anymore and we go bankrupt. And this is practice. So we try to model stopping times these two ways. And models with predictable stopping times are called structure, where we model structure. And the second, with the totally inaccessible stopping times, are reduced form models. Well, just randomness is just randomness. The second are more better for pricing, but okay, both classes of models are popular. Okay, and now the question of David, I guess. Yes, was it David? About using of, is David there? No. Okay, someone else, but it's important. It's an important issue. So define this notion that way. So probability that the company defaults after time capital T, provided sigma field at time little t. So provided information, sigma field is information. And we've got, of course, such properties that that increases with capital T, because probability of default later is smaller than default before. Yes, and Pt of t is, of course, equal 1, because probability that we didn't either 1 or 0, probability that we've already defaulted is either 1 or 0, because we know that. Yes, and the process P of t is a non-negative martingale. So, of course, we assume what the applied mathematician does, because applied mathematician assume everything is differentiable, everything is integrable. We don't have any technical problems. So if we assume that P, T capital T, is differentiable, we've got the following representation. Yes. And then again, as in the Heath-Jarrow-Morton framework, we assume that this term called hazard rate, most forward hazard rates to be precise. So forward hazard rates are Ito processes. What again is no assumptions, because being Ito process means being a continuous semi-martingale. And we've got the theorem, which is exactly of the form of Heath-Jarrow-Morton theorem. So the market is arbitrage free. So PT are non-negative martingales. If and only if this orthogonality condition holds. So the drift is of that term of the Heath-Jarrow-Morton. And the proof is exactly the same as in the case of interest rates. So we notice that this term is a martingale and use the eta formula for interest rates. So an eta process is a martingale only and only if it is its drift is equal 0. So we calculate eta formula for that term, get some blah, blah, blah calculations where something must be equal something in order to keep the drift null, and we get exactly the same result. And if hazard rates default probabilities are driven exactly by the same equations as interest rates, we are we may use any of the interest rate models, to model hazard rates. And we do. So that was a question of someone. So maybe some comments from the audience, questions. Did I lie to you a bit? I lied twice during the talk. Last 5 minutes, I lied twice. So please comment. Ladies and gentlemen, there is an issue to discuss.
Okay, there is a comment. If default can occur, can we still take zero coupon as numeraire in forward measure? That is, in fact, is a question.
Yes. So the answer is simple yes. You, of course, take zero coupon as. So that's a note, maybe not old result by Philip Schenbucher, that we shouldn't worry too much that when bonds default, their value falls to zero, because all the philosophy of numeraires dividing by zero is not a problem. Of course, if we divide 0 by 0. So it works, yes.
Another question is, the model is not differential?
What does it mean, model differential?
I don't know.
So I'm saying, no, this is what I've just told you, that all interest rates models are used for credit risk. So BGM is quite often used. Cox, Ingersoll-Ross, Bragg-Karasiński, Cheyette model, yes. And one of my lies here was that about the Hull-White model, because we may imagine negative interest rates. But of course, probabilities rarely exceed 1. Okay. Say it directly. Probabilities never exceed 1. So in the Vasicek Hull-White model, it would be probable. And how do we practitioners deal with that problem? Any guess from the audience?
There is still a question from the previous demand. It says the fault occur instantly. So does hedging work? Does hedging work?
Pardon, could you repeat?
The fault occurs instantly. So does hedging work?
Yes, I think yes. So the problem, what practitioners do with Gaussian models, for which hazard rates may be negative, so what would result in probabilities exceeding 1. So you didn't have a guess. Too bad. The answer is they don't care. They don't care, and that shows a bit how we deal with mathematical models in banks. A model is, bank employees' work is run by procedure. And at a model, we may think as a procedure. So a prescription, how input we get some numbers here, output you get a price. So the problem, if it is consistent with reality or not, is a minor problem. So its primary function is fulfilled. And that's practical probability of negative hazard rates is very small. Okay, so that is how to price credit risk options, which are few and not much liquid, and they were never liquid. So that's not what is most important in credit risk modeling. Other things are more important, namely migration from the rating classes. So for this purpose, we've got the Jarrow-Lando-Turnbull model. So the state space consists of d+1 numbers. 0 is absorbing state, representing default, and 1 to 3 up to d represent rating classes. So you know about ratings. So ratings are from AAA down to some other letters of the alphabet. So down to C. And the transition probabilities, which are given by these numbers, Q. So Q is probability that the state state process jumps from I to J. So, and they satisfy all the usual conditions for discrete Markov types in continuous time. We may do it in discrete time as well, but doesn't bring anything.
There is another question.
Yes.
Okay. Credit risk, does it mean spreads increasing or the default of the company itself? Does it protect from both?
Yeah, and that's a bit orthogonal theory to what I've told you before. Because we should expect that the spread, when the rating increases, the spread should decrease. So that is, but it's not always true. There are unexpected defaults. So if you want to buy a theory putting together transitions between rating classes and spreads and credit spreads, it would be more complex. But okay, in the Jarrow-Lando-Turnbull model, we assume that spread is stable for every rating class. In practice, it is not true, but for the purposes Jarrow-Lando-Turnbull model serves, it is satisfactory.
There is another question. Is the formula for QII here in this slide correct? Is it not 1 minus the sum?
No, no. Not 1 minus the sum. So there is one which is added and subtracted, and this is okay. So the generator looks like that. This formula, if that was for every for j equal I, we should have at I, but then I should be added here. So it's added and subtracted. Formula is correct. But good you keep in mind the theory of discrete Markov chains. And that model, so the probability satisfies, of course, these linear equations. So this is the forward Kolmogorov equation for continuous time Markov chains. And it is not used for trading, as far as I know. This is rather for regulatory purposes to calculate limits and so on, to report to regulators, because trading is a part of bank's activity and of minor importance. So the hardcore of bank activity is loan deposit is lending money. And that must be followed by some procedures. So all the companies got limits, they've got credit spreads. So that should be, that is ruled normally by rather common sense or historical approaches, but regulators want mathematics in the bank's report, and mathematics is not bad. It helps. Okay, the transition probabilities, Q, I, J, there are two ways of calculation. So one is historic. So we just take historical transition probabilities for some time period and build an estimation, or we build strange model with many copulas and other stuff, and we deduce from that. So that model is called credit metrics. It's completely nonsense, but very popular.
Sorry, there is another question.
Yes.
They say those matrix of probability transitions, they are estimated industry per industry. Are you talking about ratings by agencies?
They are
internal ratings of banks.
Both, because banks got internal ratings which are based on their own databases, but of course credit metrics was created by one of rating agencies. So rating and agencies as well publish such matrices, and independent companies publish such matrices. I think Spain is a very good country for this purpose, because I think Spain started to make this data public. So with Spanish regulations. And I think Santander and survived the crisis quite well, in opposite to other banks. So okay. Spanish regulators are good. So you may go there to work.
Okay.
Okay, so next, the problem. So I think I needed 45 minutes to tell you everything about, no, sorry. There was one more lie in the previous part. So first lie was about Gaussian hazard rates. And the second was that I didn't model default probabilities, didn't mention about interest rates here. So when default probabilities are correlated with interest rates, when hazard rates are correlated with interest rates, all formulas look slightly different. So the correlation should be incorporated in the models. And that lie was not that cruel because nobody does it in practice. You know, the credit products are much less liquid than interest rate products. So they are as far I don't know about any products which are exposed to correlation of hazard rates and interest rates. So in practical applications, we assume that they are independent. So that was the second lie. And now, so we have reduced the credit risk modeling to interest rate risk modeling. Yes, we said there is no difference between hazard rate and interest rate. So what is good for interest rates is good for credit risk. But there is one but with credit, what doesn't appear for interest rates. This is default correlation. We've got several currencies. But number of companies, of legal entities is much larger. And we are exposed to the risk of joint default of various companies, yes? So it's better to when one ugly thing happens to us, then we've got a sequence of bad events. So that is default correlation. What is the probability that defaults of two companies happen close to each other? So that is important from practical point of view, component of default modeling. So one is credit value adjustment. What is credit value adjustment? So far I assumed that there is no credit risk in the interest rate stock. So when we trade with a counterparty, we expect that all the obligations from it will be fulfilled. But that's not mandatory. Lehman Brothers collapsed, not speaking about smaller companies. And there are as well credit correlation products. To be honest, every bank is a credit correlation product. Yes, because the bank takes deposits from various entities. So from private persons and companies. And if someone defaults from time to time, that's not that bad for that bank. But a cascade of defaults would be much painful. Okay, so I think that was a good introduction for tomorrow's lecture. So
there is another question still.
Yes.
So do you treat differently default of corporations and default of